All right, so far we've talked about zero-dimensional point defects, one-dimensional line defects or dislocations, and so here I kind of want to talk about the rest. So two-dimensional, three-dimensional, and other defects in other materials. All right, so one type of two-dimensional defect is that grain boundary that we talked about before. So previously, when I talked about the difference between a single crystal and a polycrystalline material, I noted that if you have a polycrystalline material, there's going to be an interface between two grains, and those grains are not at the same orientation. So there's an angle of misalignment between adjacent grains. And because a crystal is meant to be perfect and infinitely large, any region between grains is an area of disorder or defect. And that's what we see here. So we see that when there's an angle of misalignment and we form this grain boundary, unlike the very ordered material in the interior of the grain, right at this boundary, we see a lot of open space, right? And there's a lot of mismatch between where atoms should be and where they are. And this kind of open area, this is a grain boundary. And because the angle between them is relatively high, we call this a high angle grain boundary. So the angle is relatively large. Here's an example of a much smaller one, so we call that the small angle grain boundary. And the difference is about, this is less than 15 degrees, these are higher. About that. So we're not going to talk much about the difference there, but if you ever go into more depth on grain boundaries, you'll talk more about that. But again, these are transitions between lattices in different areas. There's going to be disorder, and so there's lower density, and it has some physical effects. Because it's lower density, things can move around more easily because it's more open, and so we have higher mobility of atoms, so they can move around, and that results in a higher diffusivity. We're going to talk about this in the next chapter, and it also means that that area is more reactive chemically, and so this is something that we will use in the next section that we're going to talk about, the next module. All right, so to kind of think a little bit more about these boundaries, we kind of have to think about how they're formed. So for solidification, so if you're thinking about a liquid forming into a solid, we're going to have a liquid, and then we're going to form these tiny little particles of that crystal, that grain. And so we call the very beginnings of those crystals nuclei. And so these little tiny dots are the nuclei of the crystals. So the nuclei form, and then they grow into much larger grains, and they grow until they no longer have any liquid. And so they do that, and all of these grains are growing, and so they basically start growing until they encounter another solid grain, and that encounter is that grain boundary. So we have this sort of grain structure over here, and the growth of those crystals. And so they grow until they meet each other, and this is the result. All right, so during this formation, we can also get something called twins, or twin boundary. This is a plane, so it's a planar defect, two-dimensional. And basically what it does is it's like a reflection of the atomic positions about a certain plane. So on this side, the left, we have a crystal, and then something happens during the solidification process, or some other type of process, in which we actually have a reflection. And so you see that this other part is reflected, and so the position here is identical, is basically reflected onto here like a mirror. And the same thing for this position and this position, and etc. These two positions and these two positions, so forth. And so we call this a twin, and this is the twin plane. And because it's a defect and it's planar, that's again a two-dimensional defect. So that's another example of a two-dimensional defect. Another one that I want to talk about is the actual surface of a crystal, right? So if we consider a single crystal, and this is actually a very nice TEM, or transmission electron microscope image of a crystal, and you can see that basically these fringes, these differences in the coloring, indicates planes, right? So we're basically looking at a column of atoms in a plane, and so the spacing between dark regions is the spacing between planes. So we're looking at a single crystal material here, and these are very small crystals. And what we see is that, again, in the middle, it's perfect, right? Everything's at its given position, nothing's out of order. But when it stops, when a crystal stops, that's a defect because we expect crystals to be infinitely in all direction, which is obviously an unrealistic ask, but that's the case. And so the surface, there are atoms that are not bonded to all of the other atoms and ions that it should be. So there's dangling bonds and so forth. And so these types of features on the surface, like we see kind of represented up here, that whole surface is a defect. And there's different types of surface sites. There can be just a plain terrace here. There could be a ledge between planes. There can be a crevice. There can be what's called an adatom, a step, a kink in that step, and then a vacancy. So there's all types of surface sites, but these are all defects because it's a plane, and there should be, in a perfect crystal, more atoms on the surface. So these external surfaces are really important for the field of catalysis. Catalysis is basically a catalyst is something that increases the rate of a chemical reaction without it being consumed. So it's basically an inert material. It's basically a material that acts to speed it up but is not consumed. And so catalysis, basically these are what's happening is reactions happening on the surface. So the active sites on a surface, it could be a ledge, it could be a step, terrace, whatever it is, but those chemical reagents are reacting or on the surface of the catalyst and proceeding to give you products, but the catalyst is unchanged. So basically what happens is you absorb gas molecules, for example, onto a surface, they interact with each other and react and form products, and then are removed from the surface or desorbed. And that's kind of and I bring that up because catalysis is all about these surface defects and surface of a material. So here's kind of an example of a molecule interacting with a catalyst surface. So this is a certain molecule, and then the surface atoms are the ones here. They absorb onto certain sites like those kinks, ledges, or steps, and then they react with other chemical compounds and create products, and then the surface remains the same. All right, so that was two-dimensional defects. Well, I mentioned earlier in the section, we have three-dimensional defects as well. And three-dimensional, we're talking about a volume of material. And so this could be a pore. So a pore is just an empty spot within a lattice. So this is a certain material, and then you can see empty spots all over. So these are pores. We also have cracks. So cracks are volumes of materials that are defects. So this is on the surface. You can also have what we call foreign inclusions. These are just foreign materials, other phases, other materials in a certain material, right? So other phases, other materials. So these are all examples of volume or three-dimensional defects. So these are obviously going to play a big role in something like fracture, where we're looking at failure of materials. But we'll talk more about those as we get into that chapter. And I just want to have one end note here about defects. So defects also happen in polymers. We haven't talked about polymers yet, but when we do, this will make maybe a little bit more sense in terms of the crystal structure. But with polymers, we have chains. And so the defects kind of act differently. So they're basically defects in the chain. and the chain orders in a certain way to form a crystal structure. So you kind of see here the normal kind of chain of a polymer bending over and combining into a crystal structure. But there can be defects in that. So you can have a region like this where the chain doesn't quite align properly, and so it becomes non-crystalline. You can have two ends that don't quite meet, right? So that would be kind of like a point defect. You can have kind of this loose chain. Again, chain ends. You can have an impurity. You can have a dangling part of the polymer chain. And you can have all these kind of edge dislocations, screw dislocations. You can have a lot of the same things, but you can also have some interesting other defects like loose chains, errors in the chain grouping, and so forth.